Okay, this is it. Hopefully your last video lesson before we get back to school next week. So we've looked at ionic bonding and we've looked at covalent bonding, and in this video we're going to look at the properties of metals and how metals are bonded together. So there's really three things you really need to be able to do for this topic. And the first one is you need to be able to list the common properties of metals and non-metals. The second is that you need to be able to describe and explain how a metal is bonded together, so how it's arranged. And the third one, a little bit more difficult, you need to be able to link those two things together. So you need to be able to explain why metals behave the way they do, why they have the properties that they have, in terms of how they're structured and bonded together. So first of all, let's have a little think about the common properties of metals. So these are the things you need to be able to recall and remember. So the common properties of metals are that they are normally solids with a high melting point. So metals tend to have to be heated quite a lot in order for them to melt. They tend to have a shiny surface, especially when polished. They're normally what we call malleable, and we'll talk about what that means in a minute. They normally have a high density, and remember, the density of something is a reflection of how much mass it has in how much space it takes up. So if you imagine holding a lump of metal, you'd expect even quite a small lump of metal to be quite heavy, and that's because it has a lot of mass in a small space, so it's quite dense. An example of material with a low density would be something like polystyrene. So if you've ever unpackaged something new and it's got protective polystyrene in it, when you hold that polystyrene, it can be quite big, but it has very low mass. So polystyrene has a very low density, whereas metals tend to have a very high density. And lastly, and very importantly, metals tend to be good conductors of electricity. And we'll talk about why that is in a minute as well. So on the flip side of that, non-metals tend to have the opposite properties. So they can sometimes be solids, but they tend to be liquids or gases at room temperature. They normally have a low melting point. They're not normally shiny when they're solid. They are brittle, which is the opposite of malleable. Again, we'll talk about that in a minute. They tend to have a low density, and non-metals in general are poor conductors of electricity. And it's interesting to note as well that on the periodic table, just over 3/4 of all the elements on the periodic table, so 3/4 of all the elements in the universe, are actually metals. And whilst these properties that we're talking about are generally found in either metals or non-metals, as we've discussed, it's not always the case. There are sometimes some exceptions. So we need to talk about how a metal is structured, what it looks like at the atomic level. So metals are made up of millions and millions of atoms which are all identical. And because they're identical, including their size, they line up in neat rows, as you can see on that diagram there. So they're all lined up neatly, and they're all as close together as they can possibly be. And we call that structure a lattice, which basically just means a neatly packed grid of atoms. And you know from the work that you've done on ionic bonding that metals have either 1, 2, or 3 electrons in their outer shell, which is why they will give those electrons away to ionically bond with a non-metal. Now in our metal lattice, there's no non-metal ions for those electrons to go and join onto, but our metal atoms still give away any electrons that they've got in their outer shell. So you end up with a very tightly packed lattice of positively charged ions from the metal, surrounded by a sea of free electrons. Free as in they're free to move around. So all of those outer electrons are released by the metal ions, and those free electrons surround the positive metal ions and can move around wherever they want to go. And we also know that opposites attract. So once you get a sea of free moving negative electrons surrounding our central lattice of positive metal ions, the two are attracted to each other. So the negative electrons squeeze in and crush together the positive metal ions in the centre, and that holds that lattice together really tightly and really strong. And that's the reason that metals tend to always have a high melting point. Because remember, if you're going to melt a substance from a solid to a liquid, you have to give those ions enough energy that they can start moving apart and moving past each other. And because the metal lattice is squeezed together by all of those negative electrons crushing down and holding the metal lattice together, it's very, very difficult to overcome that electrostatic attraction. You need a lot of energy, a lot of heat needs to be added to those metal ions in order that they can start moving around, and you can therefore melt that substance. So metallic bonding, these are the key points. The metal atoms line up in neatly, tightly packed rows, which we call a lattice. The outer electrons, whether it's 1, 2, or 3 per atom, are released and given away, and we call those free electrons because they're free to move. We also call them delocalized because they're no longer local to the atom that they originated from. They can go wherever they want. And they surround that lattice and crush inwards because they're attracted back towards the positive metal ions. And that tightly packed structure with the electrons on the outside pushing back inwards makes the metal strong and difficult to melt. So the next important property of metals that you need to be able to understand is malleability. So just imagine for a moment that you have a sheet of glass. If you hammer that sheet of glass and try and bend it, the glass will just break and shatter. It's not malleable. But if you have a sheet of metal, you can hammer it and you can bend it and you can deform it and it will change shape, but it won't shatter. And if a substance can be hammered or deformed into a different shape without shattering, we describe that substance as being malleable. Now remember, we don't just want to remember a list of properties for metals, we want to explain why they have those properties using our knowledge of how the metal is bonded together. So the reason that a metal is malleable and can be hammered into a different shape without shattering or breaking is because of the arrangement of the particles. So all of those positive ions that make up the lattice are arranged in neat rows, and that allows them to slide past each other if a force is applied to them. So think about a pack of cards. If you had a pack of cards stacked up in a pile and you push against them sideways, the cards can slide past each other. And that's what the different rows in our metal lattice can do. And that is why we can change the shape of our metal without it actually breaking apart. So that's malleability. Now, the other really important property of metals is that they nearly always conduct electricity. And it's also important that you can explain why metals conduct electricity. So first of all, let's just remind ourselves what electricity is. An electrical current is simply a flow of electrons. So in order to have an electrical current, you need to have free and available electrons to flow down the wire. And we know that in the structure of our metal, those outer electrons have been released and are free electrons. So if we apply a voltage to our metal, those free electrons can flow through the metal towards the positive terminal of the power source. So it's because there are free electrons in our metal lattice that the metal can conduct electricity. If you compare that to a non-metal, for example, carbon dioxide, you know from our covalent bonding lesson that carbon dioxide is made up of a carbon atom and two oxygen atoms that are bonded together by sharing electrons. And none of those electrons from either the original carbon or oxygen atoms are free to move around. They're locked in to our covalent bond. So if you apply an electrical current to carbon dioxide, there are no free electrons available to move, and the current can't then flow through the material. So we've talked about the common properties of most metals and non-metals. We've looked at the structure of a metal, how the atoms are actually arranged and what happens to the electrons. And we've looked in detail at two of the really important properties of metals, malleability and the ability to conduct electricity. We've looked at those two in terms of the structure of the metal itself. Can we explain its behavior and its properties based on the structure that's inside that metal? So there are some questions below this video based on the content of this video. You need to answer those questions now. You might want to rewind the video and look back through it just to remind yourself how best to answer those questions. There's also a Warwick Star extension question. Have a go at that as well. And when you've answered those questions, you can submit your form, and that is the end of today's lesson. Well done, and I will see you in school on Monday.